Hello again, everyone. So this lesson, we're going to look into balancing redox reactions. So last lesson, we constructed the half reactions. And remember, this unit, we're continually building off of what we previously learned. So we started with assigning oxidation numbers, and then we went into determining who loses and gains and is oxidized and reduced in reaction, and then showing that loss or gain using the half reactions. And now we're going to look into how to balance redox reactions. So remember what a balanced reaction shows us. Now, what we've learned before is a balanced reaction shows that mass is conserved. So conservation of mass, what goes in must come out. So atoms on the left equal atoms on the right, showing us a conservation of mass. And also charge is being conserved as well too, because we're dealing with any movement of electrons that's taking place. Whatever is lost is gained, so that overall charge is being conserved. So we have a conservation of mass and charge. So now in a balanced redox reaction, we're going to express that specifically by looking at electrons, because we're not always going to see the whole picture. So in the past, when we balanced reactions, we just counted the number of atoms on each side and got them equal by adding coefficients. So now it's a little bit different. So let's use this as our example. So copy these notes down as we go, and we'll work through some practice problems, and then that'll be pretty much it. So let's start off with this. So jot this down. Now, let's write our rules down below. So skip a little space over here. So that's where we're going to do our work. And then write down these steps, and we'll go through them one by one. So using half reactions to balance redox reactions. So why are we doing things differently? Well, look up here. So we see aluminum is reacting with copper ions. So copper is not just going to be present as an ion all by itself. Really what's happening here is copper is in an ionic compound with somebody else, some negative ion that we're not seeing. So that would be our spectator ion. So we're not really getting the whole picture here. So if we did have the whole picture, we'd be able to balance it the conventional way, like we've done before, where you just list your elements down the middle, count the numbers on each side, and then work through and balance them out. But now here we're not getting the whole picture, so we can't balance the conventional way. So we have to use our loss and gain of electrons to help us out. And the whole concept here is, in a balanced redox reaction, electrons lost are going to be equal to electrons gained. So first thing we're going to do is, as we've done before, assign oxidation numbers to all the elements. So you go through, assign your oxidation numbers. Remember, give zeros to your uncombined elements right away. So aluminum and copper get zeros. And then the copper +2 and the Al +3 ions, remember, they already have their oxidation states. The charge is their oxidation state when you're dealing with ions. So that was pretty easy. We just gave zeros to the uncombined elements, and now we move on to the next step. Remember, step 2, identify the oxidized and reduced species. So we make our little connections, but we're also going to take it a little bit further. So let's make a little table here of who's oxidized and who's reduced. So draw this little table in here below the equation. And we're going to kind of use this to work through the problem and to figure out the balanced reaction. So now we connect the ones that changed. So that's step 2. We're identifying our oxidized and reduced species. So aluminum 0 became aluminum +3, and copper +2 became copper 0. So now let's put in our loss and our gain. So remember, Leo jumps up. So aluminum 0 became aluminum +3, so that's going up. So that means we lost 3 electrons. And then copper went from +2 to 0, so that gained 2 electrons. So as you can see, the loss and gain is not the same. Electrons lost isn't equal to electrons gained, and that's been something that's shown up before, but we haven't really addressed it until now. So now we're going to balance it to show that electrons lost equal electrons gained. Because remember, in a balanced reaction, mass and charge are going to be conserved. So who's oxidized? Leo says Gur. So all these things are coming up that we've used before. So remember our good old Leo jumps up and Leo says Gur, right? So all these things are still helping us out as we go along through this topic. So Al0 jumped up to Al plus 3, so that was a loss. And then copper plus 2 gained 2 electrons, so it was reduced. That's our Gur. So remember, whoever's oxidized and reduced is always coming off of the left-hand side, reactants, right? So that's step 2, just who's oxidized and who's reduced. Step 3 is to just write our half reaction. So this is what we did in the last lesson. So Al0 is becoming Al plus 3. So remember, we're just pulling it right out of the equation. So left-hand side. So aluminum 0 is becoming aluminum plus 3. All right. Now, how did it do that? By losing 3 electrons. So remember, when electrons are lost, they're leaving. So they go on the right-hand side. So Al0 becomes Al plus 3 by losing 3 electrons. So the electrons are leaving. They're exiting the equation, so they're going to go on the right-hand side. Now, copper is gaining 2 electrons. So the electrons are entering, right? They're gaining, so they're coming into the equation, so they're going to go on the left-hand side. So copper is gaining 2 electrons to become copper 0. So your electrons go on the left-hand side. So we're always adding. It's just a matter of which side they go on, just like with energy when we did energy in equation. So think about that, and all the same rules still apply. So copper plus 2 gains 2 electrons to become copper 0. So this is all review. We've done all this before. So now, step 4, we're going to multiply the half reactions by factors that make the electrons equal. All right? So I've got 3 electrons here and 2 electrons over here. So I'm showing 3 electrons lost and 2 electrons gained. So I want to get those equal through multiplication. So just like with balancing equations, if I can multiply one side by something to get it to equal the other, then I can do that. If not, then I just go to the next common product. So 3 times 2 is 6. So I want to get each half reaction to show 6 electrons lost and 6 electrons gained. So how do I do that? Well, I'd have to multiply the whole oxidation half reaction by 2, because 2 times 3 is 6, right? So now we'll just distribute that too. So 2 Al0s makes 2 Al plus 3s plus 6 electrons. So all we're doing is multiplying the entire half reaction by 2, and the goal is to get those electrons to be 6. Now we're going to do the same thing on the right side, the reduction half reaction. So we want to get 2 to 6, so we're going to multiply the whole half reaction by 3. So that gives us 3 copper plus 2s plus 6 electrons makes 3 Cu0. All right. So what was the point of doing all this? Well, 6 electrons lost, 6 electrons gained. We're all good. All right. So we're trying to get, just like we said before, electrons lost equals electrons gained. All right. That's what we're trying to do here. That's our balanced redox reaction. And now if you want, right, we'll rewrite it. So generally they'll give you some space here to write the coefficients in, and you would do so. You'll see that when we get to the practice problems, but or otherwise we can just put everything back together. So now step 5 is combine the half reactions to get the balanced redox reaction. So what do? We just kind of put the pieces back together. So Al0, so now there's 2 Al0s plus 3 coppers. So we're just kind of putting things back together. Left side of the reaction, right side of the reaction. So 2 Al0s on the left of the arrow, 3 coppers becomes 2 Al plus 3s plus 3 coppers. So we're taking things from the left side of the reaction and putting it back together, right? And then we're taking things from the right side of the arrows and putting those back together. So let's change color here. So aluminum plus 3, and then copper 0, right? So left side of the arrow, right side of the arrow, right side of the arrow. It's the same equation that we started with. So all we're really doing is adding the coefficients in. So sometimes you'll just be given blanks. And all you got to do is put the coefficients back in. So it would be like, okay, here's our 2 and 2 aluminum plus 3s. And then here's our 3 coppers and our 3 coppers. And that's the answer. So the answer is your coefficients, just like when we balanced equations in the past. All right, so that's your final answer. We balanced it. What is the point of balancing it? To show that mass and charge are conserved. So that's step 6 is just to check for conservation of mass and charge. So how do we do that? Well, 6 electrons lost and 6 electrons gained. So charge is conserved. We're good. And then how do we check mass? Well, just look at your number of atoms or ions, right? There's 2 aluminums on the left, 2 aluminums on the right. We're good. 3 coppers on the left, 3 coppers on the right. We're good. What goes in must come out. All that happened is there was that movement of electrons that took place because we're dealing with a redox reaction. That's it. So when you're done, just check to make sure that mass and charge are conserved. How do you know you're done? When you show electrons lost equal to electrons gained. That's it. So not so bad. So understand why we're doing things differently. We don't have the whole picture here. We don't know who the negative ion is that's attached to copper over here and then aluminum over here. So we can't balance things the traditional way. So we have to do it this way using our half reactions. All right, so now let's look at some practice problems. So this worksheet is attached to this assignment. So you can print it out if you want, or download it and mark it up digitally, or you can just copy these problems down on a piece of paper. There's really not much to write here. So whatever works for you. So let's look at this example. Number 1, Hg plus 2 and Ag are making Hg and Ag plus 1. So again, let's go back through our steps. So step 1, assign oxidation states. So we give our zeros to our uncombined elements, Ag and Hg. All right. Step 2, connect the ones that changed. So Hg plus 2 became Hg0, and Ag0 became Ag plus 1. So remember, our Leo jumps up. So Hg is gaining 2 electrons because it's going down, plus 2 to 0, and silver is jumping up. It's going from 0 to plus 1, so that's our loss, right? Leo jumps up. So now we want to make our little table. Who's oxidized, who's reduced. Ag0 is oxidized, and Hg plus 2 is reduced, always off the left-hand side. And then we got to write our half reactions. So Ag0 is becoming Ag plus 1 by losing 1 electron. So the electrons are leaving. They're exiting the equation, going on the right-hand side always. And then for our reduction, Hg plus 2 is gaining 2 electrons to become Hg0. So those are our half reactions that are taking place in this reaction. So now is the new stuff. We want to balance the equation. So we have 1 electron lost, 2 electrons gained. So we want to show electrons lost equals electrons gained. So we're going to multiply our half reactions by some number to get those electrons equal. So this one's pretty easy, because remember, if you can multiply one side by something to equal the other, then do so. I want to get 1 electron to 2. So all I got to do is multiply this whole side by 2. So 2 Ags makes 2 Ag plus 1s plus 2 electrons. All right? So now I don't even have to do anything on the right-hand side. I'm good. My electrons lost equals my electrons gained. So we're good. So now all we got to do is put our coefficients back in. So all we did was get two AGs, AG zeros, and two AG plus ones. So 2 and 2. All right. So Mercury, Hg, nothing. Remember, nothing means 1. So if you want to put the ones in, you can. Or you can just leave them blank. Remember, don't ever write zeros in there. 0 means nothing. Nothing generally means 1 in chemistry. So that's your answer. You're done. How do you know you're done? Electrons lost equals electrons gained. So it's conservation of charge. And mass is conserved. 1 Hg, 1 Hg, 2 Ags, 2 Ags. Done. Pretty simple. Okay? All right. So take a minute, work on these problems, and then unpause the video and check your answers. If you want, you can do these one at a time and see how you're doing. So I'll show you the answers one question at a time here. So if you want to do number 2, pause it, work on it, unpause it, check your answers, and then pause it again. Do number 3, check your answer, pause it again, do number 4. So whatever you want to do. If you want to do them all at once, go ahead, or do them one at a time. All right, so here are your answers. Number 2, those are your coefficients. So if you want to pause it again and work on the rest or keep going. Number 3, here are your coefficients. And then there's number 4. So if you got all these right, you're doing great. And that's pretty much it for this lesson. Now there's one last thing that you want to do here, and this is on the worksheet, or you can pause the video for a second, copy these down. Just make sure you copy everything correctly. There's one less concept I want to go over here. So sometimes you'll be given these multiple choice type of questions where they say which equation is correctly balanced. So what are we looking for? We're looking for conservation of mass and charge. So what are we really looking for here? Remember, electrons lost equals electrons gained, along with, look at the number of atoms and make sure that they match up on each side of the equation, the atoms or ions, right? So how do we do this? Well, we got to look at our electrons lost and gained, but you got to also account for the number of each atom or ion that's present. So like there's 2 nickels here, and there's 2 nickel ions. So when we look at our electrons lost and gained, you want to account for that too, for the total number of electrons lost or gained, and you're looking for the one choice where the electrons lost equals the electrons gained. So like number 1 here, let's look at this. So like number 1, let's look at this here. So there's 2 nickels. So nickel is going from 0 to plus 2. All right, so that's a loss of 2 electrons. But there are 2 nickels. So you want to multiply the number of atoms or ions by the number of electrons lost or gained. So 2 nickels, each losing 2 electrons, is a total of 4 electrons lost. All right, now there's only 1 iron, so it's going from plus 3 to plus 2. So that's a gain of 1 electron, and there's only 1 ion, so the total gained is 1. These aren't equal. So choice 1 is no good. Number 2, now nickel 0 again is becoming nickel plus 2. Put those zeros in there. So nickel 0 is becoming nickel plus 2, and there's only 1, right? Remember, nothing means 1. So that's a loss of 2 electrons. But now there's 2 irons, each gaining 1 electron. So 2 irons times the 1 electron gained is a total gain of 2 electrons. So 2 electrons lost, 2 electrons gained. Ding, ding. That's my answer. Choice 2. So let's just look at the other 2 choices, and see why they're no good. So nickel 0 becomes nickel plus 2. So that's, again, a loss of 2 electrons. Iron plus 3 becomes iron plus 2. There's only 1. So that's a gain of 1. Don't match up. And then number 4, we have nickel 0 becoming nickel plus 2. There's 2 of them, so that's a loss of 4 electrons. and then 2 irons plus 2 to plus 2, that's nothing. It's not changing. That's a gain of 0 electrons, right? So that's just kind of going through the rest of the choices and making sure that none of those are possible correct answers either, right? So that's it. This is, again, just reinforcing what we did today. Electrons lost equals electrons gained. That's showing that we're dealing with a balanced redox reaction. So again, why are we doing this differently? Because we don't have the whole picture here. We don't know who the negative ion is that's associated with iron here, or the nickel, or whoever, right? So we have to do things a little bit differently. So that's it for today. I'll see you next time.